Welcome to this video. In this video, I will be talking about quantum algorithms. Particularly, I will be discussing the Deutsch-Jozsa algorithm. And in the coming videos, I will be talking about Grover's algorithm and then phase estimation, the algorithm for phase estimation. I have also made a shorts video on the Hadamard test. And these will be some basics which will help us get into the idea of quantum algorithms. And in the video, I will be assuming that we all know how to process the quantum circuits, and apart from that, everything will be self-contained. So the main idea, let's get into it. The main idea is that we talk about query problems in these videos. So in query problem, what is the point is we have some function given to us, and this function is something like here, and it is from a set of binary strings of length n to output a binary string of length m, and then this function is given as a black box, and we don't have direct access to the function. What we can do is we can query to this function, we can ask various questions to this function, and then we make some output or some prediction based on these queries. And this output that I have shown here, this output basically this output is something that is related to the property of the function. So it is related to the property of f, and we will see that Deutsch-Jozsa problem is one of these query models. So this is a bit restricted model, it is not a very general computation model, and in this case these asking these queries is done by using unitary operations called query gates. So basically we talk about the oracle, which is a black box to which you pass queries and it returns some answer. So it returns some answer, and the oracle can be explained in terms of a unitary operation, which is the query gate. So what is the unitary operation? The unitary operation UF, it takes two strings x and y, whereas x belongs to the input space bit string and y is to the output space. So this is n and m, and then it outputs something like this, where x and y is made to go through a bitwise XOR operation. So this operation is called bitwise XOR, and this is the basically the query gate. So based on this, we can deduce some properties of this query gate, and particularly one of the crucial properties is that it is a unitary operation. So the idea is, first property is that if you apply the query gate two times, you get identity. This is easy to see because if you apply this the second time, you will get again XOR f of x, and if it is 2 times f of x, this is equivalent to 0. So so this is the main idea of the first property, and then it has the important property that it preserves the norm. So it preserves the norm, and this implies, or this is equivalent to the fact that it is a unitary operation. So this means that basically u dagger is equal to identity, which is also equal to u square. From this you can deduce that u dagger is equal to u. So this is the second property that is also important, and you can see that it preserves the norm in a very simple way. So to do this, you just take psi, the state, expand it in your basis xy with coefficients such that the coefficients sum to 1. You can also take an unnormalized state, it will not affect. Now you can show that the inner product psi, so this is norm square, is equal to the norm square of uf of psi. So after acting the uf, so this is the second part here, and they both are equal to this quantity here that we have. And to see this, you have to use certain ideas on how this unitary is acting on the basis state. So this I have shown in property 1 and property 2. So unitary UF acts on x by and y by x and y plus f of x. By plus I mean XOR, bitwise XOR, and similarly u dagger acts on the bra vectors in a similar fashion. So if you do this, and you can easily conclude that it preserves the norm. Okay, now we have got some basic idea of what is the query model and what is a query gate or an oracle. Now we discuss the idea of phase kickback and phase oracle. So in this case, what happens is that I have some bit string x. This is in some computational basis, and I have a single qubit, which will act as ancilla, and this passes through a Hadamard gate. So it is 1 over root 2, 1, 1, 1 minus 1, and then we apply the query gate, and then we see what is the output is. So let's proceed to the calculation. So the first state I have shown here. It is just after application of the Hadamard gate, and this is the state that I am showing here. So for simplicity, I am calling this entire state, which is a minus state, as y. So y here is just the minus state. Now suppose f of x is 0, then the query gate will add this to add f of x as bitwise XOR to 0 and 1, but because it is 0, it will be doing nothing, so I will get y here. So this is minus also, you can say. Now if f of x is 1, then I will get this XOR term, so bitwise XOR term in the second slot, so in the second system. So in this system you can see that it is 0, then I have this operation, and then 1, and this will give you 1. This is addition modulo 2, so this will give you 1 and this will give you 0. So what this means is that I can think about the entire minus state as ancilla inside a big system. So in this box here, in this box that I have drawn, so in this box I can absorb the ancillary system, and I can say is this entire thing as OF. So this entire thing is OF, and this is called a phase oracle, and what it is doing is it is taking x and adding a phase based on the output of your function. So in this case the function is from input space of 2 power n bit strings, and the output space is just 0 or 1. So the function gives a binary output, either 0 or 1. And this is the main equation for the phase oracle, and we will be using it over and over again. So what this means is that OF acting on x is simply minus 1 power f of x times x, because you can absorb, you can see the action is exactly same. So if f of x is 0, it is unchanged. If f of x is 1, then it gets a minus sign. So with this we move on. So this is the idea of the phase kickback. So this phase factor in the front is called as kickback of the phase. Now we talk about what is the action of Hadamard gate on multiple qubits. So basically, if we have n qubits and we have n Hadamard gate acting on a basis vector for n qubits, then it can be written in this particular fashion. So 1 over root 2 power n, this is like the number of bit strings possible, and then there is summation over all possible basis vectors, and this summation is such that there is a added prefactor of minus 1 power k dot x, where k dot x is a dot product, but it is called a binary dot product. So k dot x is of this form, k1 x1. So you, for example, you have 1 0 0 and 0 1 0, then you just multiply these two entry wise, so you get 0 0 0, and then you take the XOR operation. So this is the main idea. And now what is the proof of this, we will see. So the claim is that Hadamard operation on n qubits acting on a basis state gives you something like this. So we will first see how it acts on just a single basis or a single qubit state. So Hadamard acting on 0 is plus state, Hadamard acting on 1 is minus state, which can be written as 1 over root 2 0 plus 1 and 1 over root 2 0 minus 1. And now this can be in a very concise way can be written in this particular fashion. So this I have shown here. So as you can see, what I have done is Hadamard acting on alpha, where alpha can take the string 0 or 1, is 1 over root 2, which is the factor due to qubits. And then there is a sum over beta belonging to 0 and 1. So you first run over 0 and then 1. And then there is minus 1 power alpha times beta. It is just a multiplication, not a dot product. But for a single bit string, it is same. And then I have beta. So this is trivial. So this is trivial, this thing in the box. Now Hadamard acting on x bit string is like you can write x as x1 to xn. So you can write x as x1, x2, xn, where these are like 0, 1, 1, 0, 0, 1, for example, something like this. And now you act with Hadamard gate on each of this. And action of Hadamard on a single qubit we know from this trivial thing that we discussed. So this gives you this line. And now you just have to collect the minus 1 factors into something like this summation, and it already looks like a dot product. And it is kind of calculating the parity of 1, calculating the number of time 1 occurs, and then we are done. So this is kind of the idea of how Hadamard gate acts on a general basis vector for n qubits. So this property we will be using in the Deutsch-Jozsa algorithm. Now let's look at the algorithm for Deutsch-Jozsa problem. So Deutsch-Jozsa is a promise problem. So there is some promise that we are given, and the idea is it is a problem about constant or balanced function. So a constant function is a function, suppose a function is from 2 power n bit strings. It takes one bit string of length n and gives 0 or 1. And now if it always gives you 0 or always gives you 1 for any bit string of length n, then it is called a constant function. Otherwise the function can be not constant as well as not balanced also, but balanced function is such that for half of the bit string, so out of the all possible bit string, which is 2 power n possibilities, 2 power n by 2, half of the bit strings take a particular value like 1 or 0, and the other half take the exact opposite value. So for example, you have a small example here. If I have n equal to 2, so it is 4 bit strings. So you have 0, 0, it gives 1, 0, 1, 0, 1, 0, 1, and 1, 1, 0. So this function is balanced because for 2 bit string, which is 4 by 2, it gives you 0, and for the other 2 it gives you 1. And if it was the case that for 0, 1 also it gives 1, then it is neither constant nor balanced. So this is the idea of constant or balanced function. And with this we come to the problem of Deutsch-Jozsa, which says that we are given a function f. So we are given a function f and promised that it is constant or balanced. So the function that we have is constant or balanced is sure, and we just need to determine which out of these two it is. So is my function constant or is my function balanced? So classically you can think that the best is to make two queries. So you make two queries, you pass two inputs, and if the result is different, then you know that the function is balanced, because now you know that the function can either be constant or balanced, but it's giving different results for two outputs, so it must be balanced. Now worst case is that after passing two queries you see that it gives the same output. Then you are not sure that it is constant or balanced, so you need a total of 2 power n by 2 plus 1 queries. So the half of the bit strings needs to be passed plus another 1 bit string, and if you get the same result, then you know that the function is constant, because if it was balanced, then after half of the bit string it should give different result. So this is the main idea, and quantum mechanically, as we will soon see, only a single query is required to the oracle OF. So this curly O, I am calling it just O, and this is the circuit for the Deutsch-Jozsa algorithm. So you have your input as a string of n zeros. So this is n zeros, and then you have Hadamard gate on the n zeros, and then you pass that entire thing to the oracle OF, and then you have again a Hadamard gate acting on n of the qubits, and then you finally measure in the computational basis. So I will discuss each of the steps in detail. So the main idea is, let's talk about the steps, or rather I will continue the steps in a separate second video to be followed.